Okay, so end behavior of rational functions, how do we find it, and why is it good to know? Right. Remember, generally when we talk about the end behavior of a function, period, any function, we use limit notation. And uh, all this says right here is that as we're plugging in values for x that approach positive infinity and negative infinity, what's happening to f of x, and then we say what that is. So for example, right, if you're plugging in really big values for like a polynomial, right, if we had f of x is equal to I don't know, x cubed, right, and you plugged in a really big value for really big positive value for x, you would have a really big positive value cubed. So I mean, this is essentially infinity. If you take a really big number and cube it, it's basically infinity. Okay, so we would say then that this would mean that the limit as x approaches positive infinity for this function f of x, or x cubed, is infinity. And you kind of do that same analysis if you had negative, if you had, this would be, if you had negative infinity for x cubed, it would be negative infinity. And we know this is just a polynomial with an odd degree with a positive leading coefficient. And so this end behavior is typical of that kind of polynomial. Well, the same kind of thought process works for rational functions. Okay, so f of x is equal to x minus 1 divided by 3x plus 2. What would the end behavior of this be? Well, again, you do the same thing, and we could just think about this even more basically. What if x was a big number like 100, right? Even if x was 100, right? That would be 100 minus 1 divided by 300 plus 2, which is 99 divided by 302. You could put that into a calculator and you would have a fraction, you'd have you'd have an ugly looking decimal that would be very close to 1/3. If you did it with an even bigger number, if you use an even larger number for x, like let's say you use 1,000, right? 1,000 minus 1 divided by 3,000 plus 2. Well, now you've got 999 divided by 3,000. 3002, which again is almost 1/3, and it's even closer to 1/3 this time. And if you even went bigger, like let's say we use 10, we say we use a million, right? A million minus 1 divided by 3 million plus 2. That's 999,999 divided by 3 million and 2, which again is basically 1/3 for all intents and purposes. If you could imagine, if you went to infinity, you would have basically 1/3 as you plugged in values for infinity. We can't plug in values for infinity, and so what we can say about this then is that the end behavior of this polynomial, the limit as x approaches positive or negative infinity for this one, is going to be of f of x is going to be 1/3. And let's look at the graph. Okay, here's the graph of that polynomial. And you can see as you go this direction, you can see that it's getting, this is 1/3, this blue line's at y equals 1/3. And so the end behavior is it's approaching 1/3 as we get really big x values. As we get really big negative x values, again, we're approaching 1/3. One thing we can do here is realize that if I have positive infinity, if I plug in positive infinity, then I would be at just under 1/3, right? So this number here, this is just less than 1/3. It's a little bit less. If I had, when I plugged in negative infinity, right? If I had negative 1 million, million minus 1 divided by negative 3 million plus 2, this would be just more than 1/3. It would be a little bit more than 1/3. And so notice when we plug in that negative big number, we're above the line 1/3 here, we're below the line 1/3 here. That's an important observation that we can make about this. So that would be the end behavior of this one. Let's look at another one. Okay, so skip some of those intermediate steps. If I plugged in a really big value here, like a huge value, it'd be huge plus 2 divided by huge squared plus 2. This is basically like if you had 100, it'd be 100 divided by what's 100 squared? 10,000? Like this is almost 0 already. That's 100,000, but you get what I mean. That's almost 0. And so if you got bigger and bigger and bigger and bigger, effectively what you would have would be what models 1 over x. And so 1 over x, if you plug in a really big number for x, that's basically 0. It's not 0, but it basically is. So for this one, the limit as x approaches positive or negative infinity of this f of x would be 0. Okay, and let's look at the graph. You can see the blue dotted line is just along the x-axis there, y equals 0. And so you can see as we go far that direction, we have it's approaching 0. Again, from above, and we can verify that, right? If I plug in a really big positive x value, I'm going to have a value basically 0, but it's like positive 0. If I did the same thing and I plugged in a really big negative x value, right, then I would have basically 0 also, but below 0. So we're like below the x-axis over here. We're above the x-axis over here. Let's look at another one. Okay, so here if we took something like if we're squaring something, this is going to control what happens here. The 3x isn't going to mean anything. If I'm plugging in really big numbers and I square a really big number, that's such a bigger value than if I take a big number and multiply it by 3. So basically this is just x squared divided by x squared. This is just going to be 1, right? If you plug in one really big positive x value, it's going to be 1. And so the limit as x approaches positive or negative infinity of this f of x is going to be 1. And we can look at it here. Look, this line is at 1. Okay, also we know that if we went positive infinity, we'd be just above 1, right? Because if we set positive infinity, we're taking more away from this one than we are on this one, so we'd have a larger value as we put in positive infinities. If we have negative, it's the opposite situation. Okay, we'd be kind of adding more to the bottom, so we'd be slightly less than 1. There's kind of another way to think of this, and it's a little bit more of a rigorous approach, and this is something you'll learn in calculus. But if you look at the highest degree of the denominator, which is x squared, and we divide every single term in f of x by x squared. So basically f of x is equal to, and then we say x squared over x squared. I don't know why my pen is leaving these traces. Minus 1 over x squared divided by x squared over x squared minus 3x over x squared plus 4 over x squared. And we kind of simplify this a bit, then this is just going to be 1 divided by 1 minus 1 divided by x squared, all divided by 1 minus 1 over x plus 4 over x squared, right? And so we look at this and we're like, all right, well, if we plugged in really big x values, this is going to be 1, right? If we plug in 0 here, this whole term, if we plug in a really big positive x value right here, this whole term is just 0, so it's just going to be 1 on top. And if we plug in a really big positive x value there, that's going to be 0. That's 1 divided by a huge number is 0. 4 divided by an even bigger number is still 0. So that's going to be 1. And so that's kind of another way to think about what's happening with the end behavior there. However, if you keep doing this over and over again, you realize that there's a pattern, and then from that pattern you can generate some rules. Here are the 3 rules for the end behavior of a rational function. You have 3 different possibilities here, and it has to do with the degree of the numerator versus the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then the limit, the end behavior, the limit as x approaches either positive or negative infinity of this function is 0. And we saw that in an example earlier. The second one is if the degrees are equal. So you have like something like ax divided by bx, then the limit as x approaches positive or negative infinity is going to equal the quotient of the coefficients of the highest degree term in the numerator and in the denominator. So here's just this is a super basic example here. If we had ax divided by bx, well, x to the first and x to the first are the same, so the coefficient here and the coefficient here, they divide, and we have this. And we saw that in a previous example also. It was 1/3. It was the first example we just did previously. Now, obviously, there's a third scenario here, right? And that's when the degree of the numerator is greater than the degree of the denominator. And we're going to save that for the next video because it's a little more involved. But I wanted to do one quick example here of how we can use all this information to actually go about graphing a rational function. Okay, so this is a rational function, and we want to go about the process of graphing it. This is a real basic approach here. There's all these basic things apply to all of your rational functions, but then there's a further analysis we want to do on them. So first things first, the domain. We know that the domain is going to have there's going to be a domain restriction when 3x plus 2 equals 0. That's when we would be dividing by 0. So that means that x cannot equal, right, negative 2/3. And that's going to correspond to, because nothing canceled out here, that's a vertical asymptote. If we want to write the domain, it'd be negative infinity to negative 2/3 union negative 2/3 to infinity. There's a vertical asymptote at the line x equals negative 2/3 because that's excluded from the domain. We can kind of sketch that in on our graph. Negative 2/3 is like right here. Okay, so there's going to be a vertical line here, vertical dotted line, x equals negative 2/3. The graph of this function will never touch that. We can also easily find the x-intercept. We find the x-intercept by setting the function equal to 0. So right, 0 is equal to x minus 1 divided by 3x plus 2. We think, when is a fraction equal to 0? A fraction is always equal to 0 when the numerator is 0. So x minus 1 equals 0, x equals 1. That means there's an x-intercept at 1, or that coordinate be 1, 0. Y-intercepts, kind of similarly, you just plug in 0 for x, right? So f of 0 is equal to 0 minus 1 divided by 3 times 0 plus 2, which is just negative 1/2. So that means there's a y-intercept at negative 1/2. So at 0, negative 1/2. This crosses the x-axis. So let's plot that information here. We've got an we have a x-intercept at 1, 0. So that's right there. We have a y-intercept at negative 1/2, a 0, negative 1/2. So right here. And we also, we can look at the end behavior. So the end behavior of this, because these are equal, right, this degree and this degree are equal, we take the 1 and divide it by the 3. The limit as x approaches positive or negative infinity of this function f of x is equal to 1/3. So that means I can kind of draw in this, what we kind of call a horizontal asymptote at 1/3, okay? Meaning that's kind of how the end behavior of this thing is going to work. And what we can do now is that we actually have enough information to sketch in this line. We know that, one further thing we can do, right? If we look at this function, we plug in, if we took f of x and we plugged in a big positive value, right? It would equal 1/3, but it would be just less than 1/3. Because we'd be subtracting 1 from the numerator and adding 2 to the denominator, which means it's a value that's going to be slightly less than 1/3. So we actually have data down below the x-axis, way over here. Or not below the x-axis, below the line y equals 1/3. By the same reasoning, we also have data up here, because if we plug in a really big negative value, our f of x value would be slightly greater than 1/3, because we'd be subtracting from the denominator. If you have a smaller denominator, you have a larger value, right? Okay, so how can we sketch in this graph? Well, we know that this is an infinite discontinuity, and if we're crossing the y-axis here and we're not doing anything else, right? So let me use a highlighter here. If I'm crossing the x-axis right here, and I'm not crossing the x-axis any other time, that means that this line has to cross the y. It goes up along this asymptote, doesn't touch it. I know I did a bad job drawing that. Crosses the y-axis there, crosses the x-axis there, and then it's gonna just shoot off this way. It doesn't do any other funny business along the x-axis, because we know that there's only the one x-intercept. Okay, same reasoning, we know that there's no other y-intercept or x-intercept, and we know that we started up here, so the only thing that this can do is kind of shoot up that way. Shoot up along that vertical asymptote. And that, believe it or not, that's a pretty accurate graph of that rational function. If we wanted to be more precise, we could plug in like negative 2 into the function and see what that was and graph that point. And we could do that, but that's not really going to be super required for this. It's more that you understand how laying out the information that was given to us will allow us to kind of sketch in everything for the function.